introduce Will Hamilton. Will is an associate professor, an assistant professor at the McGill University. He is a Canada CIFAR AI chair, a member of Mila. He completed his PhD in computer science at Stanford University in 2018, where he received the award for the best computer science PhD thesis. Also, in 2014, he also received an award for Best AI-themed Master's Thesis in Canada. So if you're looking for somebody to give you advice on how to write a great thesis, maybe Will's choice. His research lies at the intersection of machine learning, network science, and natural language processing, and his with a current emphasis on graph representation learning. And that's great because that's exactly what he's going to be talking to us about today. So the talk is going to be live. I think he's going to have a few pause sessions to answer some questions that you'll post in the Q&A section, but he won't be able to do it in parallel as because he's giving a live talk. And then after, there'll be more of a discussion like we've previously had, where you'll be asking your questions live. So if you have sort of questions to ask along the way, don't be afraid to put them in the Q&A, but otherwise you can save more discussion-like questions for the end. All right, and with that, I'll let Will take over. Thanks for coming.
Thank you, Aaron. And yes, as Aaron mentioned, please kind of let questions accumulate in the queue as things go, and I will pause at a few sections throughout just to answer a couple questions as they come. So the topic for today is graph representation learning. And so for those of you who are not familiar with graph representation learning, the motivation and the idea behind this, a very quickly emerging subfield of deep learning, is that we want to develop techniques that can allow us to do deep learning or representation learning on graph structured data. And so what I mean by graph structured data are things like social networks, so maybe doing things like friendship recommendation, doing analysis on things like knowledge graphs or biomedical networks. Another very quickly emerging area that's getting a lot of attention is actually learning on molecule structures. So trying to analyze the structure of molecules. You can even represent the syntax of natural language or programs as graph structures, or also things like the networks of neurons. So we have all these different types of data in the world that naturally have this graph or network structure, and the challenge is designing learning algorithms that can operate with this kind of data. So I'm first going to begin with just an overview of some of the core tasks that we have within graph representation learning. And so the first task that's the most well-studied task in this area is what's known as node classification. So in node classification, our goal is that we're given an input graph where we have some labels on some subset of the nodes in this graph. So we have some entities, some vertices, which you often will call nodes, and then we have some edges which represent relationships between these nodes. And we know the information, the labels about some subset. So maybe we're on Twitter and we know that some subset of users are bots, and we're trying to use some kind of learning algorithm to infer the labels on the remainder of the graph. So an example of this in the real world could, for example, be applying machine learning algorithms to classifying the function of proteins in the human body based on the interactions between these proteins. So what's known as the interactome, which essentially is a graph representation of all the proteins in the human body and the interactions being edges between these proteins. Now the second, I would say most popular, or in some ways one of the equally popular tasks that we work on in graph representation learning is called link prediction. Here again, we're given an input graph, and our goal now, instead of trying to classify information on nodes, instead we're trying to classify information about edges. And usually how we view this is that we're given an input graph and there's some edges that we're uncertain about. We don't know if these edges exist, and we're trying to use a learning algorithm to infer whether or not these edges are actual true edges in the graph. So for example, a really important application of this in the real world is for things like computational treatment design and drug repurposing. So what you can do is you can represent, as I mentioned, the interactions between proteins as a network or graph. You can also represent the interactions between proteins and diseases, and between different chemicals and drugs and diseases, also in a larger heterogeneous graph structure. And a task we can do here is trying to actually predict whether or not there are likely to be, say, interactions between a particular drug and a particular disease. This is a way that we can try to do things like computational drug repurposing. And then the last sort of canonical task that we work on in graph representation learning is graph classification. So here, rather than being given a single input graph, instead we have a set of different graphs, and we have some label, some target associated with each of these different graphs. And our goal is to classify the label associated with the entire graph. And a very popular example of this, especially in the last 2 years, has been actually predicting the properties of molecules based on their graph structure. So trying to understand if a particular molecule is soluble, if it's stable, if it's toxic, and so on. So this idea of deep learning on graphs has really increased in popularity in the past, say, 5 or so years. As I'm showing here, this is actually extracted from Google Trends. So it's worldwide web searches for recurrent neural network, which is a very classic algorithm from deep learning. And then in blue is graph neural network. And you can see that the interest, at least as measured from Google Trends for graph neural network, is actually starting to approach that of recurrent neural networks. And a lot of that has to do with this new interest in these application areas like computational drug design and repurposing that naturally work with graph structured data. So the outline for today, we're really going to have 3 core parts to this talk. So first, I want to give a brief history introduction to graph representation learning. So trying to take you somewhat chronologically through some of the core methodological developments in this space. Following that, I'm going to try to introduce as quickly as I can the 2 dominant theoretical paradigms that we use to analyze models in this space. So trying to not just introduce the models, but also some of the theory behind these models. And then time permitting, I want to discuss 3 open problems and in some sense, 1 grand challenge for future work in this area. So a bit of a forward-looking discussion of what's next within this subfield. And for those of you who want to follow up in more detail, most of the content I'll talk about today is going to be in a book, which will be available online, hopefully in November, but there's a draft that's publicly and freely available, which is at the link shown there. So almost all the content today will be in full mathematical detail available at that link shown there. Okay, so I'm going to begin now with this introduction to this history of graph representation learning. It's a brief history also because it's a pretty young subfield. And I'm going to start off with a little bit of background and motivation and discussing how graph representation learning is in some ways different and more challenging than standard deep learning. So the goal in graph representation learning, if you want to boil it down to the core task that we're interested in, is really trying to learn useful node or graph representations without handcrafted features. So you can think about this as what you could call the node to vec problem, trying to map each node in a graph to some Euclidean vector embedding, or the graph to vec problem. And these are really the core problems that we work on in graph representation learning. And you might wonder why this problem of node or graph to vec is particularly hard, or why it's different than anything else that we do in deep learning. And the challenge here is really that modern deep learning techniques, so especially the kind of workhorses of modern deep learning, which are convolutional neural networks and recurrent neural networks, they were really designed for some particular simple kinds of geometric structures. So in particular, CNNs, they work on grids or images, and recurrent neural networks work on sequences or things like text. And the issue is that graphs really lack this regular geometric structure. And another way of looking at this, these key challenges when you're working with graph data, it's first off this issue that in graphs, there's no simple notion of things like spatial locality. So if you're in an image and you have that one pixel is a neighbor of another pixel, which is a neighbor of another pixel, then you can easily derive what the distance or a bound on the distance between the 2 other pixels. You have these notions of simple transitivity, whereas in general graphs, none of these simple geometric relationships necessarily hold. And another really interesting problem with graph data is there's this issue what we call these inherent symmetries in graph data representations. So usually how we represent a graph is using an adjacency matrix. So we'll denote that by A, And the adjacency matrix simply tells us whether or not there's an edge between two nodes. So we have a value of 1 if there is an edge and maybe 0 if there isn't. And one of the challenges when you're working with graph data is that any function we design that takes an adjacency matrix as input has to be permutation invariant with respect to this adjacency matrix. So what I mean by that is that if we apply our deep learning algorithm any function f that's going to be well defined on a graph, if we apply that function to a permutation of the adjacency matrix, we should get the same thing as if we applied it to the original adjacency matrix. And the reason for this is that the adjacency matrix tells us which nodes are connected to other nodes. And so when I apply a permutation, so by that I'm simply shuffling all the rows and columns, I'm not changing the connectivity of the graph in any way. I'm just doing an arbitrary kind of reordering of the nodes within this adjacency list, but that doesn't actually change the graph structure. And this is really important. And at the node level, the equivalent challenge that we have is the fact that any node level function, any function that's generating representations of nodes, has to be what we call permutation equivariant, which means that if we take our adjacency matrix and just shuffle the rows and columns, then the output of our model should just be shuffled in an analogous way. And this is an actual very big challenge, and it's related to a really fundamental issue in graph theory, which is a seemingly very simple problem is actually really computationally hard on graphs. And this is the problem of just trying to determine if I give you two input graphs, are those graphs the same? So what I've shown here on the right are two graphs that actually correspond to the same graph, where I've colored every node according to its degree, just for visual illustration. And the idea here is just recognizing that these two graphs correspond to the same object. That problem is very computationally hard. It's actually known as what's called an NP indeterminate problem. So we don't know any polynomial time algorithms that exist, and we're pretty sure that no polynomial time algorithms exist for it. And the reason for this is that trying to tell whether or not two graphs are the same requires that we search over all possible permutations of their corresponding adjacency matrices. So this issue of kind of permutation invariance, or figuring out the right shuffling of the rows and columns in the adjacency matrix for a graph, is actually a really fundamental problem, and is connected to this idea of isomorphism testing, which will also come up again later in the talk when we discuss some of the theoretical perspectives on GNNs. Okay, so that's just a brief history of some of the motivation of why graph representation learning is challenging. And then in this next part of the talk, I'm going to discuss some of the seminal methods that have been developed for graph representation learning, going in a rough chronological order. But at this point, I will pause for just a brief second and see if there's questions in the QA that I can answer before we jump into some of the methods. So one question here, so it was a question on recommendations for reading. I would maybe, in a biased way, recommend the notes that I posted earlier. And I would say that those notes that I posted give a lot of references to other works, which can be a useful way to dig into this field. And just taking one other quick question on isomorphism testing, and some of these other questions I will get to also in the QA session later on, is this question of, for isomorphism testing, would locally checking the immediate neighbors for each node in a parallelized way not be a sufficient method? So this is a really good question. This is the idea of, why can't we just check the local structure around each node and use that as a signature? In fact, it's not perfect, but that's one of the best heuristics that exists for graph isomorphism testing. And I'll actually discuss later on how graph neural networks can really be viewed as a particular instantiation of that idea. So that is a really good approach. It's not perfect. There's some failures for it. I won't go into those failure modes in detail, but that's a very good idea. And again, it's actually one of the theoretical perspectives that underlies a lot of the methods I'll talk about today. And then lastly, just because it's an important clarification question, is a question by Sagar here, which is whether or not graph representation learning is about learning the structure of the data or the network. So usually, this is not always the case, but in all of the methods I'll talk about today, we're going to assume that what we're given is a graph structure. So we're given usually an adjacency matrix, which tells us the connections between different nodes. And sometimes we might also have some node features or some features associated with maybe our edges. And what we're trying to do is we're trying to learn good representations, so good vector embeddings of our nodes given this input graph. So we're trying to learn embeddings given a graph. Okay, so there's a couple other great questions there, and I'll return to those later in the talk. Okay, so the first, what I'll call kind of classic approach to representation learning on graphs is what's called the node embedding approach. So our goal in node embedding is that we're trying to encode the nodes in our graph. We're trying to map all of the nodes into some low dimensional embeddings so that the dot product or some distance in this low dimensional Euclidean embedding space approximates similarity in the original graph. The idea here is somewhat similar to learning word embeddings, but rather than trying to learn embeddings for different words, we're trying to learn embeddings for different nodes. And how we want to do this is that we want to have dot products, or often distance in some sense, in our embedding space to correspond to some notion of similarity within our original graph. And in these traditional node embedding techniques, which were kind of a dominant approach in the early, say, 2010s, up until the last few years, these approaches use what I call a shallow encoder approach. And again, this is very analogous to word embeddings for those who are familiar with word embeddings. And the idea here is that we're simply defining a really big matrix called the embedding matrix, where every different column in this matrix corresponds to a different node in our graph. So we're optimizing one vector for every different node, and we want to train all these embeddings to reflect some notion of structure or similarity in the input graph. And two dominant examples that have been very popular for how we can do this, and again, here just showing a kind of high-level idea behind how these work. So first off, people have used what I'll call adjacency-based similarity approaches. So here, what you might want to do is you want to optimize your embeddings. So I'll use Z subscript U for the embedding of node U. I want to optimize these so that the dot product of the embedding for nodes U and V, so that that approximates the entry in the adjacency matrix for those two nodes. So basically you want to have this to be large if these two nodes are connected and to be small otherwise. And generally, rather than just approximating the original adjacency structure, people often will also take powers of the adjacency matrix. And what that means in terms of the graph is that you actually want your embeddings to encode how many walks there are between these nodes. So if you take the third power of the adjacency matrix and look at the entry corresponding to nodes U and V, that tells you how many length 3 walks there are between these two nodes. And this approach has done particularly well on a number of tasks. There's many different versions of it. This idea was first proposed in its kind of full version in this algorithm called HOPE that I'm citing here. But then probably the most dominant and popular technique in this area, there's one algorithm called Deep Walk, another that was called Node to Vec, both of which are quite popular. It's a similar idea of trying to encode information about walks or distances on the graph. But rather than trying to just encode the information in the adjacency matrix, instead, we want to have the dot product between the embedding for two nodes to correspond to the probability that those two nodes co-occur on a random walk over the graph or network. And again, this is the idea that's implemented in the algorithm called Deep Walk, as well as later on in an algorithm called Node to Vec. Okay, so that's a very quick overview of these, what I'll call traditional node embedding methods. I'm giving just a quick overview of them here because I want to spend most of the time today on what are called graph neural networks, which are more of the deep learning algorithm on graphs. But before getting to graph neural nets, it's worth talking about the limitations of these traditional node embeddings and the kind of motivation for why we need to design things like graph neural networks. So the first issue with these traditional node embedding algorithms, so you'll recall that the idea here is we're defining an embedding matrix where we have one column for every node in our graph. So we're optimizing a unique embedding vector for every node so that we can capture the structure in our input graph. And this is really not very parameter efficient. So in particular, if we have V nodes in our graph, then we need V columns in this embedding matrix. So the number of parameters that we need in our model grows with the size of the graph. Another related issue is this issue that these techniques are inherently what we call transductive. So what this means is that if I optimize my node embeddings on an input graph, and then this graph grows, or I get a new graph, I don't have embeddings for any of these new nodes. I need to retrain my model, and I can only really get embeddings for nodes that I've already trained my model on. So we call that this issue of these models being transductive. And then lastly is this issue that these node embedding techniques, all they do is try to learn the structure of the graph, kind of as represented by the adjacency matrix. They don't learn anything about any, say, features that we might have associated with our nodes. And very often, the graph data sets that we work with actually have interesting node features. So there's no natural way to incorporate those in these algorithms, and that's a major downside. So what I'll discuss now as an alternative, and which has really become, at least in the last few years, the dominant paradigm within graph representation learning, this idea of what are called graph neural networks. So to make things precise, when we're talking about traditional node embeddings, here we're simply trying to map every node to its own unique embedding vector that is just determined via some loss function, say based on random walks. Whereas in a graph neural network, the way that we're encoding a node, so the way that we're mapping a node to some embedding, is actually going to be a complex function, so some kind of deep neural network that is a function of both the adjacency matrix of the graph, as well as the matrix of node features that we have. So now we're taking as input to our model the adjacency matrix, so which tells us the connections between all the different nodes, and we're also taking in as input the matrix of node features. So we're assuming that all the nodes have features. You can also assume that edges have features, but I'll just keep things simple here and assume that we have features on our nodes. And the idea behind graph neural networks, I think, is best described, so first off in this visual illustration, and then I'll actually give the mathematical definition in the next slide. But the idea here is that if we're trying to learn a representation for some target node, so here I'll call this node A in this input graph, the representation that we're going to learn for node A is going to depend on information that A is aggregating from its local neighbors. So here nodes B, C, and D. And then the information that B, C, and D are kind of sending to A, as what we'll often call a vector message, is going to in turn depend on their neighbors. So here node B has neighbors A and C, and so on. And so at every layer of this graph neural network, every node is aggregating information from its local neighborhood using a neural network operator, and then it's passing this information on to its neighbors. And so what I'm showing here is a two-layer version of a graph neural network. And once we get down to the final layer, the initial messages that we input to our graph neural network are just our initial node features. So in terms of math, which some people prefer the math, some people prefer the illustration, the idea with the basic graph neural networks, this was first proposed in a series of works by Scarcelli as well as Marco Gori in the early 2000s, and then the seminal work called the Graph Neural Network Model in 2008. And the idea here is that we're going to initialize what I'll call the layer 0 embeddings for all of our nodes as being equal to our input node features. If we don't have node features, you can just use something like the node degree or some other structure feature. And then to get the embedding of a node at the kth layer of a graph neural network, this is going to be some nonlinear function of information that we're aggregating from this node's neighbors. So here we'll just take the sum of the neighbor embeddings from the previous layer. And then we'll also take this node's representation from the previous layer. We'll multiply these both by some matrices, put this through a nonlinearity, and that gives us our new node representation. So one thing you'll note is that this looks a little bit like a simple recurrent neural network, but the idea here is that I'm not just taking information from the previous time step in the RNN, I'm aggregating information from all the neighbors in the graph. So how we actually train a graph neural net, so how we actually take this technique and use it to generate high quality representations, there's two different ways of doing this, and we're really just going to try to define some useful loss functions on the output of our GNN. So again, what we're trying to do here is we're actually just trying to train these matrices that we're using to aggregate information from our local neighborhoods. And what we're going to do generally, just for notation wise, is I'll assume that after I've run k layers of my graph neural network, I'll take the output of that final layer and I'll call that my final node representation. So I want to define some loss functions on this final Z subscript U node representation that I can use to train all the parameters and all the layers of this GNN. So the first option that we can use is we can just try to train graph neural networks in an unsupervised way. So we can try to say train our graph neural network so that the embeddings that we learn can be used to reconstruct the adjacency matrix. One particularly powerful approach that's worked well in recent years, this idea of what's called self-supervised learning on graphs. So this is very similar to what's called the BERT algorithm and other algorithms that are very popular now in natural language processing. But just to give you the high level idea of how we train graph neural nets in an unsupervised way, so without any particular labels on our graph or on our nodes, is that we'll take our original input graph and then we'll make a corrupted version of that graph. So we'll take our graph and then we'll maybe perturb some of the edges. And then we'll get embeddings of our nodes in the original graph, as well as in the corrupted version of that graph. And then we're going to train a discriminator model, so some neural network, which is trying to distinguish which embeddings came from the original graph and which embeddings came from the perturbed graph. So it's an idea that's kind of similar to something like a generative adversarial network. It's kind of similar to techniques that are very popular right now in NLP, like the BERT algorithm, but we're trying to train our model to essentially learn to distinguish between our original graph structure and perturbed versions of that graph structure. So that's one option, is to train things in an unsupervised way. But an alternative here is that we can also directly train the model using a supervised loss. So for example, if I have labels on my graph that tell me, say, if it's a social network, that we have particular nodes that correspond to humans or bots on Twitter, and we're trying to classify whether or not they're a human or a bot, we can just use those labels and use something like a binary cross entropy loss, so your standard supervised learning classification loss, to solve this. And here the idea is we're simply taking the output embeddings from our graph neural network, and we're treating those as the input features essentially to a small logistic regression or a standard neural network, and training the whole model end to end using something like stochastic gradient descent or your favorite algorithm, say in TensorFlow or in PyTorch. Okay, so just to quickly talk about some of the advantages of graph neural networks. So the first big advantage of graph neural networks is the fact that the number of parameters is independent of the graph size. So if you're looking here at the parameters that we have in our graph neural network, they correspond to these matrices that we're using to transform the information that we're aggregating from local neighborhoods. So the dimension of these matrices is only dependent on the size of our input features and the size of our hidden embeddings. It doesn't matter how many nodes we have in our graph, the size of our graph neural network in terms of the number of parameters stays the same. And again, one way to look at that in terms of this visual illustration is that our graph neural network is corresponding to these little boxes, which are essentially neural nets that tell us how to aggregate information from local neighborhoods. And when we're aggregating information for every node, we're just replicating these same boxes, these same parameters over and over again. And another useful thing, while I have this up, is just to note that the depth of a graph neural network also corresponds in some sense to how far out in the graph we're searching. So if I have a 3-layer graph neural net, that means that every node is aggregating information from 3 hops, so from nodes that are at most a distance of 3 away in the original graph. So it's an interesting kind of interpretation that depth in graph neural networks is not just like depth in a regular, say, CNN or MLP, in that it actually has this interpretation in terms of the original input graph. So in terms of other key advantages, so another thing with this idea of having our parameters be independent from the graph size, this also means that graph neural networks are what we call inherently inductive, so that I can train a graph neural net on one input graph, and then if I have another graph that has the same type of node features, I can apply my graph neural network on that new graph, even if I haven't trained on it. So I can apply these GNNs to graphs I haven't seen before, to nodes that are added to my graph, and so on. This is a really powerful feature of graph neural nets compared to these traditional node embedding techniques. And the last feature that really makes graph neural networks particularly attractive is also this idea that they're truly a classic deep learning algorithm, in the sense that they can be end-to-end incorporated with different models. So we can apply different kinds of supervised loss functions. You can even do something like take a CNN to generate embeddings of images as your node feature. So suppose you're trying to analyze data from a social network that is profile pictures. You could use a CNN to generate embeddings of the profile pictures to get node features, and then use your graph neural network on the output of those CNNs and train this entire model end to end. So these graph neural networks are really like the analog of CNNs or RNNs, but for graphs. And so we can mix and match to them as much as we like with the other types of algorithms that we have in our deep learning toolbox. So what I described in the last few minutes is really what I'll call the basic graph neural network. If we want to generalize this idea and discuss what is the kind of modern implementation of GNNs that is quite popular today, this approach is often what's called the neural message passing formalism. The idea is that we can kind of generalize this notion of aggregating information from neighborhoods into this idea that we want to learn an updated embedding for our node at, say, the kth layer of our graph neural net as being some function of information that we're aggregating from this node's neighbors. And then we're also going to have some update function, which takes the message, as they'll sometimes call it, that we're aggregating from the node's neighbors, and combines this message with the information from the node's previous representation. So we can generalize most modern graph neural networks as being a combination of an aggregate function, which tells you how does every node aggregate information from its local neighborhood, and then an update function, which says, how do I take this aggregated neighborhood information, combine it with the node's current representation, and use that to get a new embedding for this node. And there's been a large number of different techniques proposed in terms of generalizing both this neighborhood aggregation and this update idea. So for example, one popular approach for aggregating over neighborhoods is rather than just summing over your neighborhood, you can actually use an attention approach where essentially you learn which neighbors you want to pay attention to. There's other approaches where rather than just summing over your neighbors, you're instead going to take all of the neighbor representations, transform them using an MLP, so using a neural network, and then take the average of those transformed representations, and so on. So there's been a large number of different techniques. They all have this flavor of averaging or taking the sum or even taking the maximum over information from the set of neighbor embeddings. And there's many different things that you can try here. The other place where you can generalize this idea of graph neural networks is in this update function. So how do we take the information that we've aggregated from our neighbors? So I'm denoting this as the message M from the neighbors of node U. And how do we combine that with the node's current representation? So one really powerful approach is actually using things like gated recurrent units or LSTM units to do this update. This is what are called gated graph neural networks. And there's also techniques that are similar to residual connections or skip connections that are quite popular with convolutional neural networks, where we take the update function to get our new representation, but then we actually make our new embedding some mixture of the old embedding and the new one, which can actually help stabilize the learning in our GNN. And again, here, there's been dozens of different proposals for how we can generalize this update operation. And the key idea is that this operation just needs to take the information from our neighbors and combine that with the node's current representation to give you something new. And a few other useful tricks that I'll mention. I shouldn't call them tricks, they're really quite grounded methodologies. But the one idea which is actually very powerful and a very simple idea is a technique which is called jumping knowledge, or JK connections. So one thing that I quickly mentioned is this idea that generally when we define a graph neural net, we're assuming that we're taking the embedding, the node embeddings from the final layer as our output embedding. So we run capital K GNN layers and then just take the final layer output as our node representation. But what researchers have found in the past 2 or so years is that if you actually define your final node representations as a function of all of the intermediate GNN layers, this is a much more powerful model. Similarly, people have discovered that you can leverage higher order neighborhood information during each round of message passing. So rather than just aggregating over your neighbors, maybe at every step of message passing, you aggregate over your neighbors and your neighbors' neighbors. There's also a number of techniques for incorporating edge and graph level features during message passing. Now, just to close out this section, this methodological discussion of GNNs, I want to quickly talk about graph classification. Because one thing you may have noticed is that so far I've been talking about learning node representations, aggregating over node neighbors, but what if we actually want to get an embedding of the entire graph? So what if we want to do graph level classification and not just work at the node level? So the idea here is we actually need some way to combine all the node embeddings in the graph to get an embedding of the entire graph. And the simplest way that we can do this, that actually works surprisingly well, is we can simply sum up all of the embeddings that we have in the graph and use this summed embedding, or sometimes the average embedding, as our representation of the graph. There's also been some more sophisticated approaches that try to do an analog of pooling like you see in convolutional neural networks. And the idea here is that you run your graph neural network on your original graph, then you use the learned representations from your GNN to cluster all the nodes together. And then you make a coarsened graph, where now in this coarsened graph, every node corresponds to a cluster in the original graph, and you run another graph neural network and so on. So this is just this idea at a very high level. But again, there have been a number of different proposals for how we can do this kind of hierarchical pooling. And the idea here is essentially that we're running a graph neural network on our input graph, and then we're learning or determining a coarsened version of that graph by pooling or collapsing some nodes together, and then running another GNN, and so on. And so this allows us to do something similar to the pooling layers that we see in convolutional neural networks. Now, before I talk a little bit about theory, I'm just going to mention some of the impact this technique of graph neural networks has had. So one area where GNNs have been very impactful is in drug design. So here we might want to do something like combine reinforcement learning algorithms. So some of the techniques you'll hear about over the course of this week, where we're going to use graph neural networks to learn representations of molecules, and then use a deep reinforcement learning algorithm to try to then optimize over these molecule representations to actually try to find molecules that are useful for treating certain diseases. And I'm having a link here actually to a paper in the journal Cell, which showed that you could use this technique to predict novel antibiotics. And this technique is very exciting. There's been a lot of interest because it has the potential to actually really speed up the drug development and the drug repurposing pipeline. So typically it can take many, many years to find promising drug candidates, but by combining reinforcement learning with something like GNNs, we can hopefully speed this up from, say, being 5 to 20 years to find a promising molecule down to maybe something like half a year or 1 year. And there's actually been a number of initiatives building on this idea to actually try to develop new treatments for COVID-19. And here I'm providing a link down this to one of these initiatives that is being led actually at Mila by some colleagues there. The other place in the real world where graph neural networks have had a really big impact, and the last example I'll give, is recommender systems. So many online social platforms, things like Facebook, Pinterest, Twitter, can be represented as a graph. And for example, during the course of my PhD, I collaborated with Pinterest, which is a website that allows people to collect different content that they're interested in on the web and collect it into what are called boards. And we used a graph neural network approach to analyze the Pinterest graph, which contains billions of nodes, and actually use this to recommend pins to users. And we were able to get a substantial gain compared to the prior state-of-the-art in recommender systems using this approach. Okay, so that was a quick overview of graph representation learning, roughly chronological, trying to give you an idea of some of the core techniques that have been developed, as well as some of the key tricks that we use to make GNNs perform better. I'm going to discuss in the next 15 or so minutes some theoretical perspectives on GNNs. And before I do that, I'll see there's a number of different questions, so I might just have to pick and choose one or two. And I'll apologize, this will be somewhat arbitrary. So one question here is actually on applications of graph neural networks to NLP, and I'll answer that because I had a slide on that and I actually removed it at the last minute. Indeed, there are applications in natural language processing. So you can usually, one of the most popular applications is using graph neural nets on the syntax structure. So things like the dependency tree or the constituency parse of a sentence, but also lots of applications where you combine graph neural networks with something like a knowledge graph to do better, say, question answering. And another, this is another question which I do want to answer because it is I actually see there's two questions related to this, and I think it's worth answering. This is this issue of this idea of message passing. Doesn't this lead to an issue where we have some kind of infinite recursion, where we have something like a loopy belief propagation where everything is depending on everything else, and then we have recursion in our computation graph? One of the key ideas in the graph neural network message passing is that the embeddings at the kth layer or the kth iteration of message passing only depend on the representations from the k-1 layer. And so in this way, even though every node is aggregating information from their neighbors at every step, the structure of the computation graph actually ends up being a feed-forward tree. So it's kind of a little bit of a thing to wrap your head around, but the key idea is the idea that we're not having any dependency between node representations at the same layer. So every node, when it's aggregating information from neighbors, that's only depending on the information from the neighbors at the previous layer. So this means that we don't end up with any actual kind of recursive loops in our computation. And it's a really key element of what makes graph neural nets work. And there's some other actually really great comments in there I'm seeing as well. And one comment that was posted was asking about the typical depth that is used for GNNs. And indeed, as was answered by Chris, typically papers will use 2 or 3 as a typical depth. And I'll hopefully have the time to talk a little bit about some of the theoretical reasons why we need to use relatively small depths in our GNNs. Okay, so now turning to some of the theoretical perspectives on graph neural networks. And I'm going to forewarn that this is going to get a little bit more mathematical than the earlier slides. And some parts of this will hopefully be interesting pointers for you to dig in more if you're interested in it. And I'm going to try to get across some of the high level ideas, but I hope please don't be intimidated by some of the terminology, because it is going to take a little bit of terms and methods and ideas from some areas in mathematics like graph theory and harmonic analysis that can be intimidating at first, but I promise if you dig into it a little bit, it's actually quite a lot of fun. So the two dominant theoretical paradigms that have been used for investigating GNNs. So first off is this idea of thinking about graph neural networks as actually being a generalization of convolutions to non-Euclidean graph data. There's this idea that graph neural nets are really like convolutional neural networks that have been generalized. The second way that graph neural nets have been analyzed is based on connections to graph isomorphism testing. And in particular, the idea that graph neural nets are actually very related to a traditional approach to isomorphism testing. So I'm going to give a quick overview of both of these areas to hopefully give you a little bit of the insight of these two quite distinct theoretical perspectives, and then maybe some insights about the relationships between these two different perspectives. So the intuition for how we can view a graph neural net as really corresponding to a convolution is this idea that if you imagine running a graph neural net on a grid graph, so if you think of an image, it's really just a grid where we have a bunch of pixels that are connected to one another. So if you think of running a graph neural net on such a grid graph, it would actually correspond to something like a center surround filter. Every pixel will be looking at information from its neighboring pixels, and those neighboring pixels will be looking at information from their neighboring pixels, and so on. So this is this intuition that you can think of graph neural nets intuitively as corresponding to something like a convolutional filter. But really, actually, in a theoretical sense, GNNs can be derived as a generalization of the convolution operation to the graph domain. This is based on this idea of what's called graph Fourier analysis that I'm going to give a quick primer on, because I think it actually is very interesting to not just discuss graph neural nets from the perspective of these deep learning modules, but also understanding some of the deeper mathematics that's involved. So in terms of graph Fourier analysis, I'm going to focus on a few key facts that we need to understand how a graph neural network can be viewed as a convolution. So the first idea is this idea that we can define what's called the Laplacian operator for a graph. So I'm going to define what's called the symmetric normalized Laplacian just because it makes the math most clean, but there's other variants of the Laplacian. And the idea here is that the symmetric normalized Laplacian, denoted by L, is simply the identity matrix minus the symmetric normalized adjacency matrix. So basically, we're just taking the adjacency matrix, we are normalizing all of the rows and columns by the degrees, and then we're going to take the identity minus this matrix. And the reason why this matrix is important is because if we have a signal, so we imagine that we have a signal on our graph, which is really just a vector where we have one value for every different node. So we can say the value of this signal at node U is equal to 5, at node V is equal to 6, and so on. If we take a signal on the graph and we multiply this signal by the Laplacian matrix, what this does is this measures the difference between this signal at each node and its neighbors. So taking the adjacency matrix L times some signal, so some basically feature matrix X or feature vector X, is going to tell us the difference between every node's feature or its signal value and the signals in its local neighborhood. And since this is the normalized version, it's going to be normalized according to the node degrees. Now, an interesting fact is that this graph Laplacian is not something that just comes up out of nowhere in a vacuum in graph theory. The graph Laplacian is actually the discrete version of what's called the Laplace operator on Euclidean space. What's also known as the Laplace-Beltrami operator in more general Riemannian manifolds. And the idea in terms of the math is that the Laplace operator on a continuous Euclidean space is defined as what's called the divergence of the gradient of a function. Now, the details there aren't critical. What's critical is the intuition that the Laplace operator on graphs and the Laplace operator on Euclidean space, what they do is they measure the difference between a function value or a signal between a point and its immediate neighborhood. So in a graph, that's the graph neighbors. In Euclidean space, that's an infinitesimal neighborhood around each point. Now, A third very interesting and very deep mathematical fact that I will not be able to prove in any satisfying way here is the fact that if you look at this Laplace operator and you look at the eigenfunction, so the generalized notion of an eigenvector of this Laplace operator, it corresponds to what are called the Fourier modes. So basically the eigenfunctions, the generalized eigenvectors of the Laplace operator are the different plane waves. So basically the different waves, sine waves that we can have in Euclidean space. And why this is important is if we're thinking about Fourier analysis, the fundamental technique in mathematics, one way of viewing Fourier analysis in standard Euclidean space is that we're taking some function or some signal and we're projecting or representing that signal on the eigenbasis of the Laplacian. That's one very formal mathematical way of thinking about Fourier analysis, is that this Laplace operator, we're looking at this operator, looking at the eigenfunctions of this operator and trying to understand how to represent a signal based on those eigenfunctions. In more kind of classic simple terms, we take a signal and we represent that signal as being the sum of a number of different frequency waves, but all these different waves correspond to the eigenfunctions of the Laplacian. So the key idea in graph Fourier analysis is that we can generalize this notion of taking a Fourier transform by basically trying to do the analogy in graph space. So whereas in the Euclidean regular signal processing world, when we take a Fourier transform of some function or some signal, we're representing that on the eigenbasis, representing that as sinusoidal waves. Here, we're going to represent this as the eigenbasis or the eigenvectors of the graph Laplacian. So in particular, if we take our graph Laplacian, and we take the eigen decomposition of this graph Laplacian, so we diagonalize this in the classic way from linear algebra, here we're now getting the eigenvectors, the eigenbasis of the graph Laplacian. And again, the graph Laplacian is just the graph version of the more general Laplace operator. So whereas in regular Euclidean space, a Fourier transform is a projection to the eigenfunctions of the Laplace operator, in a graph, we're going to do the same thing. We're going to project to the eigenvectors of the graph Laplacian. And it's quite a complicated kind of stream of facts and mathematical intuition. But at the end of the day, all we're actually doing to do what's called the graph Fourier transform is we're taking the eigenvectors of the Laplacian matrix and we're multiplying our input x by the transpose of those eigenvectors. And that's what's called the graph Fourier transform. And the inverse of that is just multiplying by the eigenvectors themselves. So a graph convolution can then be defined by element-wise multiplication within the graph Fourier domain. So the core definition of a convolution in regular Euclidean CNN world is a convolution is some function that corresponds to element-wise multiplication in the Fourier domain. So here we're going to do the same. We're going to do element-wise multiplication within the graph Fourier domain, and then we're going to do the inverse graph Fourier transform to get back into our regular graph domain. And one of the other things that this means is that a generalized, what we can call graph convolution, can be represented as the element-wise multiplication of this transformed version of our input times some filter in our graph Fourier space, which will often represent element-wise multiplication as regular matrix multiplication by a diagonal matrix. So that was quite fast. I have a reference up there for the draft of my notes, which goes over this in a lot more detail. But the key interpretation or intuitions here is that the Laplacian eigenvectors of a graph Laplacian are the same thing as the Fourier basis, the same thing as different sinusoidal waves in a regular Euclidean space. And in a similar way, the eigenvalues of the Laplacian are the analog of different frequencies. So you might wonder what all this has to do with graph neural nets. And the key idea here is that in practice, you can define a graph convolution as a polynomial of the normalized adjacency matrix. So in particular, we have this nice mathematical fact, which is that any polynomial of the adjacency matrix, so if I take my adjacency matrix and I take that adjacency matrix and I add it to a squared and so on, that would give me a polynomial of it. Any polynomial of my adjacency matrix can actually be simultaneously diagonalized with a Laplacian, just means it has the same eigenvectors as the Laplacian. And what that means is that if I multiply any input vector x by a polynomial of the adjacency matrix, mathematically, that's equivalent to taking the graph Fourier transform of my input, multiplying it by a signal, by a filter in graph Fourier space, and then taking the inverse graph Fourier transform back. So it's this interesting fact that it was a lot of mathematical facts and details to get to this idea that if I multiply some input by a polynomial of my adjacency matrix, mathematically, that is equivalent to a graph Fourier transform. And interestingly, this idea of multiplying by a polynomial of the adjacency matrix is actually the intuition behind aggregating over neighborhoods in a basic GNN. So if I have some input node features x, and I multiply these node features by the adjacency matrix, that is equivalent to taking the sum of the information from all the node neighbors. If I multiply by the square of the adjacency matrix, I'm aggregating over 2-hop neighborhoods. So really this idea of multiplying node features by the polynomial of adjacency matrix is the same idea of aggregating over node neighborhoods in graph neural networks. It's just a much more mathematical and formal way of deriving this idea. And what this means is that many graph neural networks, not all, but most graph neural networks can really be viewed as a combination of simple graph convolution filters, so aggregating from neighborhoods, which is multiplying by the adjacency matrix, and then combining these graph convolutional filters with linear projections and nonlinearities, just like we do in a CNN. Okay, so that was a crash course in graph Fourier analysis to give you a bit of a sense of how something like graph neural nets can also be derived in a very formal way. Now, I'm going to very quickly give you an introduction to the other theoretical perspective on GNNs, and this is based on what's called graph isomorphism testing. So the high-level idea here is the idea that graph neural nets are really a continuous and differentiable version of a really classic graph isomorphism algorithm. Now you'll see right away that it seems strange that graph neural nets are both a generalization of convolutions and also a generalization of this classic isomorphism algorithm, but I believe there's actually a very deep theoretical connection between these things. So I'm going to go over this relatively quickly, and again, there's more detail on this in my notes, but one of the key techniques that's been around for more than 50 years in terms of how people actually detect whether or not two graphs are isomorphic. This was actually asked in a question much earlier in my talk. Is this idea of what's called the Wishfire-Lehman or the WL algorithm. So how this algorithm works is that we're going to run what's called this vertex coloring algorithm, where what we do is for every node, we're going to color that node according to its degree. And then every node is going to look at its neighbors and say, what are the colors of my neighbors? And then I'm going to give myself a new label based on the colors of my neighbors. And then we're going to iterate this process again. And I can say, okay, what are the colors of my neighbors now that I have these new colors, and so on. And so you can iterate this idea of every node aggregating the colors of its neighbors. And then at the end, you're going to get a representation of your graph based on all of the different sets of colors that you end up with after iterating this algorithm over and over. And the key idea here is that graph neural nets are just a continuous and differentiable version of this algorithm. In the WL algorithm, at every step of the algorithm, every node looking at the discrete colors in its neighborhood and is giving itself a new label or a new color by hashing this information. In a graph neural net, at every iteration of a graph neural network, every node gets a new embedding using some neural network function of the embeddings in its local neighborhood. And in fact, you can prove that a basic GNN is as powerful as this classic WL algorithm. Any two graphs that can be distinguished by this WL algorithm can also be distinguished by a basic GNN. And in fact, we've proved something in the other direction, which is the fact that graph neural networks are no more powerful than this WL algorithm. So in fact, there's a tight relationship between this classic 1950s algorithm for discrete graph isomorphism testing and the power of graph neural networks. They bound each other. And there's been a number of works in recent years that have actually tried to generalize this idea beyond the WL algorithm to what's called the KWL hierarchy. But in the interest of time, I won't go over that in detail. So given that we have just 15 minutes left, I'm going to actually quickly just jump into a discussion of some of the open challenges within graph neural nets just for 2 to 3 minutes, and then I'll open up for a full QA and try to get to as many questions as I can. Okay, so what are some of the really important directions in terms of pushing forward research in graph representation learning? I think it's important not just to think about what's out there now, but also what can we do to try to build new kinds of techniques. So one idea which is related to what I just discussed is this idea of trying to actually understand how we can build graph neural networks that can go beyond what I call this WL hierarchy. So we know that graph neural nets, there have been many papers published in the last 2 to 3 years, which show that graph neural nets are no more powerful than the traditional isomorphism testing approach. There's been some other algorithms that have pushed graph neural nets to be slightly more powerful in some particular ways and so on. But I think it's really interesting to consider how we can actually build graph neural networks that really go outside of the box and are in a totally different space compared to these WL algorithms and this theoretical box that our graph neural networks right now are somewhat stuck in. Another really interesting challenge with graph neural nets, which is related more to these convolutional ideas that I discussed as well, is this challenge that's what's known as over-smoothing. So there was a question asked in the Q&A, which was about the fact of how deep graph neural networks generally are. And generally, graph neural networks are only 2 to 3 layers. That means that we're only aggregating information from 2 or 3 hops in the graph. And the empirical reason for this is that when we build deeper graph neural networks, they don't work. And the reason why they don't work is that if I build a 50-layer graph neural network, at the end of the day, the embeddings that I learn, they all look the same. The embedding for every different node in the graph, they all just look the same. And the reason for this is that when we run a 50-layer graph neural net, that's really similar to having a 50-order polynomial of the adjacency matrix. I'm essentially multiplying by the adjacency matrix 50 times. And what happens when you do that is that you're basically magnifying the influence of the dominant values in this adjacency matrix. So when you take really high powers of matrices, the high powers of the matrix get dominated by the largest eigenvalues. And interestingly, from a signal processing or graph signal processing perspective, these dominant eigenvalues correspond to something like a low pass filter. They're kind of an uninteresting corresponding to just taking the lowest frequency information, which essentially in the worst case is just a constant over the entire graph. So we know theoretically that when we simply stack graph neural nets, the current graph neural nets that we have in a naive way, we end up just learning uninteresting things. Unlike regular deep learning, where deeper networks can learn more interesting functions often, deeper graph neural networks, in some sense, theoretically learn less interesting functions. And this is a really big issue, and I think, again, points to this challenge of trying to come up with new kinds of architectures on graphs that don't have this inherent issue. And lastly, I just want to point out something that's a bit more maybe intuitive, and this is this idea of the fact that if you look at the structure of a graph neural net, we end up with this tree structure where every node's aggregating information from its neighbors. And again, as this tree gets deeper and deeper, it's going to fan out as a tree does and grow exponentially. But we're trying to cram an exponential amount of information into each of these different message passing operations. And it becomes a really big computational bottleneck. It's really hard for us to learn when we have a 50-layer graph neural net, because the number of leaves on a depth 50 tree is just giant. And there's no way to account for all that information in the later layers of message passing. And in my view, really all of these challenges I've mentioned, this idea of going beyond this isomorphism, WL idea, this idea of trying to solve this over-smoothing polynomial the adjacency matrix issue, and the problem of the inherent bottleneck in tree-structured computation graphs, I really believe that these are all indicative of kind of one underlying issue, which is how we've designed graph neural networks up till now. And I think the future of graph representation learning is going to take understanding the relationship between these different problems and also building techniques that can go beyond them. And so with that, I will switch to taking questions. I apologize, I only have 10 minutes, but hopefully I'll take as many questions as I can. And if Aaron wants to jump in to help moderate.
Great, thank you very much. That was great. So I think what we're gonna do is, just quickly take questions with people whose hands are up. If you click, Will, on the participants button,
yep.
You'll see people in the attendance whose hands are up.
Yep.
Like Tamid, do you want to go ahead and ask your question?
Can you hear me?
Yep.
So my question is, we can use GNNs to predict whether or not the two nodes are adjacent, like predicting the edge between, whether or not there exists an edge between them. So can we generalize this? Like, we're given a set of nodes and node features and use them to predict the structure of a graph.
Yes. Yeah, that's a really, really interesting idea. And I think this idea of trying to predict not just edges, but kind of more higher order connections and more complicated structures is one of the most active areas in, I would say, unsupervised learning on graphs. So there's a lot of techniques that have come out recently based on ideas. So for example, what's called the deep graph infomax algorithm or the infograph algorithm. And that's the idea that they're trying to implement. It's very challenging, but exactly that idea is, I think, the most active and fruitful direction for unsupervised learning on graphs.
Cool. All right, thank you. Ankur? Yeah.
Yeah, hello. Can you hear me?
Yep.
Yeah, so my question is, as in the graph, while building the graph, so we are building the graph for a kind of a particular node. Say for a node A, we are having a different graph. For predicting the embeddings of node B, we are having a different graph. So while training or making the embeddings for different nodes, do we have to train n different graphs for each node?
That's a great question. So generally, no. So in particular, depending on how you implement it, and there was also a question that came up much earlier that was on different frameworks. So there's one really well done framework that's supported, I believe, by Amazon, but it's open source, called the Deep Graph Library, DGL. There's one from TensorFlow called, I believe, the Graph Library. I can't remember its exact name. But in these frameworks, they'll kind of handle the parameter sharing for you. So in the simplest way, in some sense, even though every node has its own computation graph, you can share the computation and you don't need to replicate everything. But it gets challenging in terms of memory costs. If you want to have no redundancy in computation, you need to store the entire graph in memory at all times. So there's a trade-off. So if you're willing to store the entire graph in GPU memory, then you have no redundant computation. Basically, you reuse all the intermediate computations and everything is very fast. If your graph is too big to fit in memory, then you can do kind of just looking at the local graph around each node and do them all separately, but you end up wasting computation. So it's a trade-off. I think it's kind of a space-time trade-off.
Yeah, thank you.
Thanks, Diganta. Yeah.
Oh.
Diganta, yeah.
Hello, can you hear me?
Yeah.
Yep.
Okay, I have two questions. One of them is I couldn't exactly understand why would the problem of understanding the agency matrix be NP indeterminate, since the node connectivity would be in the order of the factorial of the number of nodes, which should be finite. So why do you think?
So it's, yeah, so that's a great question. So the key issue there is that by NP indeterminate, we mean that because it's n factorial, so it's essentially exponential in n. So we know it's exponential and not polynomial. So by NP indeterminate, that doesn't mean it, NP indeterminate are generally viewed as, I guess, easier than NP hard, but harder than P. So a great example of an NP indeterminate problem is factoring integers. So it's hard. We know it's very hard, but it's not an NP complete problem, for example. They're kind of a funny complexity class, but it's not that they're super exponential. They're still just exponential. Like we do know exponential time algorithms for them.
Right. I had a follow-up to that, if that is okay. Which is in the first slide, in the first section, you discussed a bit about link prediction. I would just like a comment on that. I could relate that to transfer functions, since graph structures resemble quite a lot of signal flow graph in control theory. So is that one of the inspirations for predicting link connections?
That's interesting. So there has been some work on those connections, but actually most of the work, so there's been some interesting connections relating to that into transfer functions in recent years, but historically link prediction was actually mostly motivated by social network analysis and friendship recommendation. Was actually historically where link prediction arose, and also recommender systems actually.
Awesome, thanks.
Thanks. Gabrielle?
All right, you should be able to hear me now, yeah?
Yeah.
Since a deep neural net is essentially a graph, can graph neural networks be used for architecture search? I can imagine that maybe a big DNN is very, maybe it doesn't fit into memory and you would have to do some tricks in order to make it fit, but I don't know, has this been done?
Yes, so I believe it has been done, and I'm trying to think of a particular citation. I am quite confident that I did see a paper on that recently, but I can't remember a citation. It has been done. One other thing that's worth mentioning is that I believe there is some early work on neural architecture search where the algorithms that they developed for encoding the structure of the architecture end up looking a lot like a GNN, even though they didn't call them a graph neural net. So that's also happened. I didn't talk about this in detail, but there's been many different graph neural net-like models that all kind of emerged around 2014, 2017. So my guess is that there's a lot of work on NAS that is graph neural network-ish, but didn't actually use the terminology, say, of graph neural nets.
Okay. Tolga?
Can you all hear me now?
Yeah.
Okay, thanks for the presentation. Coming from a signal processing background, I think I've most appreciated the theoretical aspects of the presentation, although it's the most math-heavy one. It seems like there's this greater notion of defining convolutions on different mathematical objects, and those yield certain things. I think I've seen, beyond graphs, I've seen group convolutions and ring convolutions, etc. I was wondering, it seems like based on the intelligence problem we're trying to solve, we're making a set of certain assumptions which yield certain mathematical objects, but is there like a blueprint on what we can define a neural network? Graphs being one of them.
That's a really good question. And I think you really point to this fact that graph representation learning is really adjacent to another subfield, which I would sometimes call geometric deep learning, for example, which is really more concerned with this idea of generalizing convolutions to other kinds of objects. And then it's adjacent to another area, which is kind of at the interface of differential geometry and deep learning, which is really saying for different types of symmetries in my data, what are models I can define that satisfy those symmetries. And what's interesting is that right now it's a really active area of trying to think about what are practical symmetries or data that we want to generalize convolutions to. I don't really think, it's almost a good way there's no exact blueprint right now, but I think if you're kind of looking at what are recent trends at some of the conferences, especially kind of trends in some of the workshops and subfields that I participate in, these kind of ideas of generalizing convolutions with different kind of mathematical operations, it's a really active area right now. Hasn't quite been kind of blueprint level yet, but I think there's a lot of things that haven't been done yet. We have things like spherical CNNs, we have generalizations of convolutions to Riemannian manifolds, but there's a lot of interesting complicated geometric objects. But maybe the one key thing is, depending what kind of work you want to do, you might care about whether or not the geometric objects or symmetries actually have real world importance, I suppose, is something to keep in mind.
Cool, thanks. That's going to have to be our last question for this session. Thank you very much, Will. That was fantastic. We have, there's obviously some open questions here that we can maybe get you to answer offline. And there's also going to be the get session with you, I think a little later that's going to happen.
Yep, so it'll be at 4, so I'm happy to.
That's right. Perfect, great, thanks.
Awesome, thank you.
Thank you. Yeah, Nadine will
just wanted to say a quick break, and we'll follow up with Alexei's talk. Will be back at 4:15 for his breakout. We'll try to get those answered during the smaller group chat with Will. Thank you so much.
Awesome. Thank you.